In this video, we'll be talking about a second way to define a product of two vectors, where instead of asking that this product return a scalar, we ask that it return a vector. And consequently, this product is called the vector product. It's also called the cross product, a more common name. So again, as in the last video, instead of simply giving you the answer right away, we think for a while and imagine how we might define a cross product. First of all, if it's going to return a vector, that vector, like any vector, has to have a direction and a magnitude. And so we have to think about how we might find or choose the direction and magnitude of the vector. One of the most natural questions to ask is to say, well, if this is a vector, which direction is the vector going to point? So let's think about direction first. And here, we're simply going to make a choice. We're going to choose the direction of this vector. In principle, one could imagine it pointing different kinds of ways, but we're going to choose that it point in a direction that is orthogonal to the plane formed by the two vectors A and B. That means it's perpendicular to both of them. And there are two possible ways that a vector could be perpendicular to both of the component vectors. It could point this way, or it could point this way. And so to resolve this ambiguity, we use, again, the right-hand rule. And we say that if we're multiplying A cross B, that the resulting vector C will be perpendicular to A and B in the same way as the right-hand rule coordinate system are constructed, meaning we point our arm out in the direction of A, we curl our fingers in the direction of B, and consequently our thumb will point in the direction of C. So this right-hand rule will enforce the direction of the cross product. And this has a very interesting immediate consequence, which is that the cross product, unlike the dot product, is not commutative. Okay, because if you imagine the right-hand rule, A cross B means we go arm, fingers, thumb points up, but if we were doing B cross A, we would do arm, fingers, and in our right-hand rule, our thumb would be pointing down. So B cross A and A cross B point in opposite directions, which means they're not the same result, which means that the cross product doesn't commute. Another consequence, or at least another dilemma we face, we'll show the following more rigorously later, but because the right-hand rule, say you have two vectors pointing in the same direction, A and B, you can point your arm in the direction of the first of those vectors, A, which points in the same direction as B. And so how do you curl your fingers? Do you curl the fingers up? Do you curl the fingers down? Do you curl the fingers to the side? You can sort of, there's no defined obvious way to curl your fingers to try to get them to point in the direction of A, because B points in the same direction as A. So the right-hand rule operation is not defined if the vectors are parallel. Consequently, the direction of the cross product is not defined. And the only way we can resolve this dilemma, if the direction is undefined, is if the magnitude happens to be 0. Because if the magnitude is 0, then it doesn't matter which direction the vector is pointing. It doesn't have any length, and so it's not pointing anywhere. So this right-hand rule construction of the dot product sort of suggests that parallel vectors will have a 0 cross product. And we'll see that that is true once we obtain a formula for it later on. Okay, so that was the direction of the cross product. Now let's talk about the magnitude. And the magnitude, we can infer a few things. We can obtain a few things by sort of playing around with different ways of constructing vectors and requiring that the cross product obey some of the rules of basic arithmetic, like we did with the dot product. Okay, so first we want the cross product to be associative with respect to scalar multiplication. If I have a CA, a longer version of A crossed with B, that should be the same as that constant C times the original A cross B. And it should also be the same as A cross the same longer version of B, scaled by the same proportion as A was over here. So you should be able to take this constant C in and out of the different terms in the cross product without changing the value of the cross product. In terms of the magnitude, this has the implication that if I increase the length of C, it increases the length of the cross product. Also, if I increase the length of B, it increases the length of the cross product. We call this relationship bilinear, that the cross product is linear in the length of A here, and it's also linear in the length of B over here. And so that imposes the constraint that the magnitude of the cross product be proportional to the magnitude of A and proportional to the magnitude of B, like we saw with the dot product, times perhaps some function of the angle between the vectors that is as yet unspecified. But we already see that this scalar multiplication associativity requires that the cross product will have some sort of relationship like the dot product had in terms of its magnitude. So now we can think about this unknown function f of theta, and it is likewise constrained if we require the cross product to be distributive. It's not commutative, but we'd like it to be distributive such that a cross b plus c is the same as a cross b plus a cross c. So now we're going to draw a triangle like we did last time. We're going to add up two vectors b and c to equal a vector a, which allows us to write c equals a minus b, like we did before. Here we're going to also sketch a translation of c from here down to here, and a translation of b from here down to here. This will just help us when we're taking different kinds of cross products. So as before, we're going to kind of do things to this equality, this statement right here, that are not immediately obvious why we're doing them, but it turns out that they reveal sort of interesting properties of the cross product. So the first thing we're going to do is we're going to take the cross product of both sides with either a or b here. We just randomly choose b, c cross b on the left, and on the right, a minus b cross b. By the distributive property, this right-hand side becomes a cross b minus b cross b. We're sort of getting a little ahead of ourselves, anticipating that b cross b is going to be 0, because otherwise, how do you define the direction? So we'll use that anticipated fact to cross off b cross b. That tells us that c cross b must be a cross b. And then imagine taking magnitudes of both sides. We would get magnitude c, magnitude b, some function of the angle between them. What is the angle between c and b? Well, that is easiest to see if we use our redrawn vector over here that we sort of translated, because the angle between b and c is this one right here, which is gamma plus beta. Then on the right-hand side, a cross b is magnitude a, magnitude b, f of the angle between them, which is gamma right here. All right. Beta plus gamma is 180 minus alpha by the triangle rule. This is a triangle that angles sum to 80 degrees. So what we're left with is f of 180 minus alpha over the magnitude of a, if we cross out the b's and divide both sides by magnitude a, magnitude c, equals f of gamma over magnitude c. Now this looks kind of familiar. This looks kind of like the law of science. So we would have been wanting to find a function f that satisfies this relationship for any pair of sides in the triangle. Turns out there is a function, sine, that satisfies that relationship for any pair of sides in the triangle. And not only that, but the sine function has the property, here you can see a little bit of a discrepancy. We've got f of 180 minus alpha compared to sine of alpha. But indeed, sine of 180 minus an angle equals sine of that angle. That's a property of the sine function. And so we'll go ahead and assume that this function f is sine theta. Now, this has been a little bit of a hand-wavy, I won't even really probably use the word derivation. Pure mathematician would really laugh at me. But sort of a hand-wavy argument to get us to a geometrical definition of the cross product without first giving you an arithmetic formula. And that geometric definition is this, that the cross product is a vector with magnitude given by magnitude A, magnitude B, sine theta, and with a direction chosen using the right-hand rule. So it kind of looks similar to the dot product in that you have this kind of relationship with a trigonometric function here, but the major difference, of course, is that it's a vector, and the direction of that vector is given by this unit vector here, which is obtained using the right-hand rule. So that was kind of long. perhaps not entirely rigorous, but I wanted to give you another one of these senses that this is not just some arbitrary geometrical, not some arbitrary mathematical object that was invented, but really once you assume that it's going to produce a vector and it's going to satisfy basic rules of arithmetic, you're really sort of constrained, and you do sort of naturally get this definition. An interesting thing that's worth pointing out before we move on is what the cross product does to basis vectors. So it's hard to communicate this without being able to show you my hand, but if you imagine pointing your arm in the x direction, curling your fingers in the y direction, then your thumb points in the z direction, and so I cross j is k. They both have magnitude 1, the angle between them is 90, and so this becomes 1, 1, 1 in the formula up here, and so you just get 1 times k, k being the unit vector pointing in the perpendicular direction. And so that's quite interesting because we order the coordinates in the order I, j, k, and if we tau a I cross j, we get k. And this continues further. If you point your arm in the y direction and curl your fingers in the z direction, your thumb will point in the x direction, just like the right-hand rule indicates coordinate axes should be ordered. And so j cross k equals I, and similarly k cross I equals j. And so this is called a cyclic relationship. If you take any two of the basis vectors in order, the result of their cross product will be sort of the next one in the list. If you imagine this list just kind of repeating I, j, k, I, j, k, I, j, k. When you're moving to the right on that list, when you're taking the cross product of basis vectors in sort of positive or right-handed order, you get the next item in the list. On the other hand, if you take cross products of vectors in the opposite order, you get negative those basis vectors. So if I cross j is k, if you imagine pointing your arm in the y direction, curling your fingers in the x direction, you'll find your thumb pointing in the negative z direction. So j cross I is negative k. Similarly, k cross j, negative I, and I cross k, negative j. So if you're taking cross products in sort of the opposite order, then you get negative signs in front of your results. So we now have enough information to obtain a computational formula for the cross product. Many books just start with that, but I like to kind of introduce some basic geometric reasoning, which then naturally gives you the formula in Cartesian coordinates. So here it is. Just like we did for the dot product, A cross B, we're going to figure out what that means by expanding A and B in IJK form, taking the cross product, and applying the basic rules of arithmetic. So again, we have 3 terms here, crossed with 3 terms here, and the distributive property says we're going to get 9 terms in the result. Those scalars, associative scalars can come out of a product, and so A1I cross B1I is going to be A1B1I cross I. And similarly, A1B2I cross J, and so on, all 9 of these terms. Just like we saw with the dot product, some of these can simplify, right? This parallel property, again, we haven't yet established that at this point, but that parallel property that we anticipate that parallel vectors will have a 0 cross product means that this term will vanish, and this term will vanish, and this term will vanish. And then the cyclic relation of the basis vectors says that I cross j is k. So this becomes k, and I cross k is reverse cyclic. That's going to give us negative j, and so on. All right, and so we can simplify all of these cross products that we have up here of the basis vectors into a simpler relationship down here. We've got some 0 terms that go away, and then we have some common factors. We have an I hat and a negative I hat, so we can collect those, and we get A2B3 I hat minus A3B2 I hat in this term right here. And similarly, collecting the j terms and the k terms, we get this long definition of the cross product. All right, now this, if you do it enough, you will eventually memorize this, but it's kind of long and it's hard to remember. And so, fortunately, there is a way to make it easier to remember. if you're willing to bend the rules of what a matrix means. And that is to note that if you could stick these basis vectors inside of a matrix, this result here would be equal to the determinant of the following matrix. If we write I hat, j hat, k hat in the top row of the matrix, we write the components of the A vector in the second row and the B vector in the third row. And then we took the determinant, we would get this result. So to remind ourselves about determinants, that would be for a 3x3 matrix, the determinant can easily be calculated by drawing sort of diagonal lines. I hat A2, B3, J hat A3, and then you wrap around B1, K hat A1, B2. Those are the positive terms up here. And then you have negative B1, A2, K hat, B2, A3, I hat, and B3, A1, J hat. This is easy to remember. It's kind of procedural. Write the ijk, write the first vector, write the second vector, take the determinant. You get this. You do have to be a little careful in certain kinds of coordinate systems. This result no longer holds, and you have to write down the long form. But it certainly makes it much easier to remember Cartesian coordinates, so it's worth remembering that. Okay. We've said a lot of things about the cross product. We have defined a geometric definition of the cross product right here. Magnitude A, magnitude B sine theta times a unit vector obtained using the right-hand rule. We have an arithmetic formula for the cross product. Now it's time to talk about why we use the cross product. Before we do, it's worth noting a few things. Is that the cross product is really sort of strange. As you go through your homework, the first few times you do this, you'll find it a little bit awkward to work with. It's definitely harder to remember and think about than the dot product. And it has some weird properties that you have to keep in mind when you're working with it. First of all, we already mentioned that B cross A points in the opposite direction as A cross B. Now that we have a definition for it, we can verify that in fact these are exact opposites. B cross A is negative A cross B. Which means that the cross product is what we call anti-commutative. It's not commutative. You don't get the same thing when you switch the order of the vectors. In fact, you get the exact opposite. So just have to remember that. Two, this is actually almost more concerning. It's also not associative if you're talking about vector multiplication. It's associative with respect to scalar multiplication, but not another cross product. So if I imagine doing A cross B cross C, you'd like to be able to move those parentheses around and say that's the same thing as A cross the quantity B cross C. But in general, this just isn't true. For instance, you can try messing around with simple basis vectors, and you can say I cross J cross J. Well, what's I cross J? That's K, and K cross J is negative I. Well, now if you try and move the parentheses around, you have I cross the quantity J cross J. But of course that's 0, and so the whole thing is 0. And so these two things are not equal, and so the cross product is not associative. Again, just something you have to remember. You cannot change the order in which these things are done. Finally, the cross product is only defined in 3 dimensions. You can't do a cross product in a 2D coordinate system, or if you imagine reaching into higher dimensions, 4 and above. Again, there's no such thing as a cross product in these dimensions. It's only in 3 dimensions. So there's some weird properties. Nevertheless, the cross product appears all over the place, and that's simply because it's incredibly useful for reasons that we'll now explore. Okay, first is this parallel property. Indeed, parallel vectors have a 0 cross product because the angle between them is either 0 or pi, and so when we plug this into the formula, A, B, sine theta, the sine of 0 is 0 and the sine of pi is 0, and so the magnitude of cross products of parallel vectors is 0, so the cross product itself is 0. Let's quickly verify that. Suppose I ask you to compute the cross product of these two vectors. First example of the day. 1, 2, 1, negative 3, negative 6, negative 3. So I write my little matrix, ijk, 1, 2, 1, negative 3, negative 6, negative 3. And I now imagine taking these determinants. So I have I hat times 2 times negative 3. That's negative 6 I hat. And then what other I hat term do I have? I have this one, minus negative 6 times 1 times I hat. Well, that's plus 6 I hat. So I hat times negative 6 plus 6. I have j hat, j times 1 times negative 3, minus negative 3 times 1 times j. So that's j hat times negative 3 plus 3. K hat, 1, negative 6, minus a negative 3, 2, k hat, that's negative 6 plus 6 k hat. All of these vanish, and so the cross product is 0. And that tells us the vectors are parallel. In this example, you can see that. You can simply observe that this second vector here, which we could call b, is negative 3 times a. But it's better to compute the cross product because you might not always notice that one vector is a multiple of another. For instance, if the second vector is 12/17 of the first vector, it might be a little bit harder to just spot that. And so the cross product is a good replacement in situations like that. So that's useful. You can use it to determine parallel vectors. Far more useful is a feature that is a result of our choice of the direction of the cross product, is that the cross product can be used to create a vector perpendicular to two other vectors. It comes straight from the definition, the way it points. So for instance, in this example, find a vector perpendicular to both the vector 1, 0, 0 and the vector 1, 1, 0. So in the three-dimensional coordinate plane, here's that first vector 1, 0, 0. Here's the second vector 1, 1, 0. They're both in the xy plane, so it's perhaps not surprising that the result points in the z direction, but let's go ahead and compute it. I times 0 minus 1 times 0 times I. Those are both 0, and so we have no i's. J times 0 times 1 minus 0 times 1 times j. Again, both 0. And finally, k times 1 minus 1, 0, k. So that's a single k, and the cross product of these two vectors is just k. So that allows us to find this vector perpendicular to the other two. We'll find that to be very useful when we talk about the geometry of lines and planes in the next section. Another incredibly useful property, and you will not believe me when I say this, is to find the area of a parallelogram. Suppose I draw a parallelogram. I've got a vector A, I've got a vector B, and then I imagine sort of copying that vector A up here, and I copy this vector B over here. And I've now obtained a parallelogram. Well, the area of a parallelogram is simply base times height, and the base is simply magnitude A. So the area of the parallelogram is magnitude A times the height. All we need to do is find the height using trigonometry. If the angle between these vectors is theta, then sine theta is h over the magnitude of A, and so sine theta is h over the magnitude of B, and so h equals magnitude B sine theta. So we can replace this h with magnitude B sine theta. Lo and behold, that's the magnitude of the cross product, and so the area of this parallelogram is the magnitude of A cross B without doing the trigonometry. Now we can just compute arithmetically the cross product and claim that that is related to this geometric property of the parallelogram. You probably have not had to calculate the area of a parallelogram since you learned the formula for the area, and you would probably not believe that this could ever be a useful thing, but it turns out that it will be crucial for doing something called surface integrals later on in the class, and so we will see that about 2/3 of the way through the class. For now, let's just use this property to do another example, which is probably far more common. Rather than computing the area of a parallelogram, this problem asks you to compute the area of a triangle between 3 points, A, B, and C, with coordinates given here in the problem. Now this is actually pretty interesting because all kinds of things calculate the areas of triangles. Computer graphics represent things using bunches of little triangles, and so it's easy to imagine that you might want to know the area of a triangle. And if those 3 points are distributed in 3 dimensions, it's really hard to think about how you might calculate the area. And so this formula of the cross product in the parallelogram becomes very handy because a triangle is just half a parallelogram. Let u be the vector AB and v be the vector AC. This triangle is 1/2 of the parallelogram, and so the area of the triangle is 1/2 the magnitude of the cross product of u and v. So all we need to do is create the vector u, which is the displacement from A to B. We get that by subtracting essentially the point B minus the point A, really vectors to B minus a vector from A, and that'll give us the vector from A to B. So 2, 4, 4 minus 1, 2, 1 gives us this vector u, 1, 2, 3. Similarly, we want to compute this vector v. We do that by subtracting the value of C minus the value of A. That gives us a vector from A to C, and we get 4, 1, 1. We compute that cross product. We have our ijk, 1, 2, 3, 4, 1, 1, and we do our diagonal lines for our 3 by 3 matrix determinant. You'll get better at this as the class goes on. We have I times 2 minus I times 3. So 2 minus 3i, j times 12 minus 1 times j, and k times 1 minus 8 times k. That gives us the vector minus 1, 11, negative 7. The area of the triangle is half the magnitude of the cross product, so we compute that magnitude, we divide by 2, and we get the area of the triangle. There's one more thing, 2 more things actually. The first thing we need to say about the cross product is we can combine a cross product and a dot product to give us something called the scalar triple product. If I have A cross B, that gives me some vector. I can take the dot product of that vector with a third vector C, and that will give me a scalar. It turns out that this scalar triple product is associative in a way. You can sort of trade the order of the dot product and the cross product in the scalar triple product without changing the result. That's related to properties of the determinant. But basically, if A cross B is ijk and then A row and then B row, the dot product of that with C is to take the I component of A cross B and dot it with the I component of C, the J component of A cross B with the J component of C, and the K component of A cross B with the K component of C. And the easiest way to do that is simply replace the ijk row with a C row. And here we've also sort of shifted them around in a way that doesn't change the value of the determinant. So it's really equal to this one here. A dot B cross C is the determinant of this matrix formed by putting the 3 vectors in the 3 rows of a 3 by 3 matrix. So that's a way of multiplying 3 vectors together. It turns out that this has another very interesting geometrical property. It is the volume of something called a parallelepiped, which is fun to say, implied by the edges A, B, and C. And then we make copies of these edges and we get this sort of sheared cube that's this 3-dimensional region. So the volume of a parallelepiped is equal to the base times the height, just like the area of a parallelogram. And that base we could call A. We know it is itself a parallelogram, so the area of the base is magnitude A, magnitude B sine of this angle theta here. And you get a vector that points in this direction straight up in this picture. And then the height is from some trigonometry. It is the magnitude of this vector C times the cosine of the angle theta 2. Gives us the height of the parallelepiped. Now, the cross product, A cross B, equals magnitude A, magnitude B, sine theta 1, times u right hand. That's just the area times u right hand. So we could write A cross B dot C is the area times magnitude of C times cosine theta 2. That's just area times height, which is a volume. All right, so this cross product, this scalar triple product here, A cross B dot C, gives us volume of a parallelepiped. Again, you would never imagine that this is an important thing, but it turns out it's extremely useful in computing things called volume integrals that we'll talk about later in the class. This has been a very long lecture. There's a lot of little things about the cross product, so I apologize. This will be one of the longest videos in the class. Last example, just for completeness, to complement the work example that we did for the dot product, is torque. So torque refers to the forces exerted to cause something to rotate around a center of rotation. So imagine like a lever that's anchored to some point in space, and you push on the lever, and you want to turn the lever by pushing on it. And you probably know that the best way to rotate a lever is to push straight against perpendicular to the lever itself, and we're about to see why. So the definition of torque is it's the magnitude of the cross product of the displacement vector from the rotation point to where you're pressing on it with the force vector, which is the force you're exerting at that point on the lever. And according to the definition, this is magnitude F, magnitude D, sine theta. We can immediately see why you point the force perpendicular to have the greatest chance of turning the lever. Because the magnitude of the cross product is magnitude F, magnitude D, sine of theta, and sine of theta has a maximum when theta is 90. So when this angle is 90, you get the most torque. This is why bicycles are designed so that you're exerting the greatest force of your legs when you're pushing on the pedal, when the pedal forms a right angle with your leg. Internal combustion engines are designed so that the exploding gasoline inside the engine exerts its force just when the lever connecting the piston to the crankshaft forms a 90-degree angle, and so on. This is sort of a common feature of lots of mechanical systems. So one last example. Here's kind of a physiology example involving torque. So suppose your forearm is 25 centimeters long. Here's your forearm. And your bicep attaches 5 centimeters from your elbow. And the goal is to figure out how much weight you can lift given the strength of your bicep. So suppose your bicep can exert 500 newtons of force. How much mass can you lift through this 135-degree angle? You're sort of down at the bottom, and then you're lifting it through this angle on your way up to do a curl. Suppose this is the hardest part, and the question is, how much mass can you lift through this angle? So this is in the torque section. We're evidently going to need to calculate some torques. Indeed, there's actually 2 torques in this problem. Your forearm has a rotation point here at your elbow. Your bicep is exerting 1 torque on your forearm, and mass, under the force of gravity, is exerting a 2nd torque in the opposite direction, farther away. So what we need to do is calculate the two torques and see for what value of the mass the 2 torques are equal, and that will be the largest mass you can lift. So what's the torque exerted by your bicep? Well, we'll just use the geometric definition. Magnitude of the force, magnitude of the displacement, sine of the angle. The angle here is 135. The displacement is 5 centimeters, and the force is 500 newtons. So we multiply all those things together. Sine of 135, that's root 2 over 2, and we get this number here, 1250 root 2 newton centimeters. What is the torque exerted by the mass in the other direction? Here the angle between your forearm and the direction of the force is 45 degrees. The displacement is 25 centimeters, and the magnitude of the force is approximately 10 times the mass, really 9.8 times the mass, but let's call it 10 times the mass in newtons. And so we have 10m times 25 root 2 over 2. That's 125 root 2 m newton centimeters. Now we have to just equate them, and we can see that mass equals 10 kilograms will give us an equality there, which means that 10 kilograms is the most mass that your bicep can lift with that amount of strength. Thank you for watching.